Hello friends, we are discussing radiative heat transfer between surfaces. So far in this course we have focused on black and grey surfaces. In this lecture we will focus on radiative heat transfer between non-grey surfaces. So, the grey surfaces are basically defined as where the emittance does not depend on wavelength. So, epsilon lambda is equal to epsilon. Okay. So, the emittance is constant over a surface, over a wavelength. So, such a surface is defined as grey. So far we have only discussed grey surfaces and black surfaces with diffuse and specular reflection. Now, we will look at the surfaces when these surfaces have different magnitude of emittance over different spectral range. What you see in this slide is basically an approximation of the emittance variation with wavelength. As we have seen in our lecture on properties of materials, the emittance may actually vary continuously over the wavelength. So, for some materials it will be constant at long wavelength region, while varying sharply in the short wavelength region, while for some other materials it may be constant at short wavelength region and then decrease at long wavelength region. But in this example or in this course we will mainly focus on materials that have variation of emittance with wavelength in the form of bands. Okay. So, as is seen in this slide, in these figures, the emittance for surface 1, let us say this is surface 1, has large value at short wavelengths and almost negligible at long wavelength, and for surface 2 the emittance is negligible at short wavelength, while it has large value at high wavelength region. So, although emittance is a function of wavelength, but we have taken a simplified case where wavelength is basically constant over a given wavelength region. So, the analysis for this type of problems will be very similar to what we have done for the grey surfaces. The expressions that we have derived for heat flux Q and radiosity Ji are equally valid for this case also. The only thing is now we will have to solve for heat flux for each wavelength for each surface, and we have to solve for radiosity for each wavelength for each surface. Okay. So, the expressions that are developed are valid here. The only thing is we have to basically do a spectral calculation. So, this is called spectral flux, spectral heat flux, and this is called spectral radiosity. Okay. So, we use the term spectral to basically define that the quantity is valid only for a given wavelength. So, the relations that we have already developed, I am just reading them again. So, we developed this relation for a grey surface where there was no dependence of any quantity on wavelength. Now, when we have a non-grey surface, all the quantities, be it flux, emissive power, radiosity, irradiation, or even the emittance, has to be taken into account for each wavelength. Okay. So, the first expression, the first equation gives you spectral heat flux, that means the heat flux at a given wavelength divided by emittance, spectral emittance, again this is at a given wavelength, is equal to a spectral emissive power minus summation over all n surfaces in the enclosure. So, we are basically talking about enclosure divided into n surfaces. So, we have j is equal to 1 to n, total n surfaces, and then we summed over all the surfaces, radiosity j lambda j radiosity, spectral radiosity of each surface, and the view factor. The view factor is purely geometric, so the wavelength does not appear in this. Okay. So, we have a view factor, a geometric view factor, and then irradiation. Irradiation again may depend on wavelength. Okay. So, this is the energy balance for a surface at a given wavelength. We have expression in terms of radiosity and emissive power. We can basically eliminate the irradiance here. So, we can write the heat flux as q lambda I epsilon lambda I times E b lambda I minus j lambda I. So, this is the emissive power and this is the radiosity. Now, we can eliminate the radiosity as we have done for gray and black gray surfaces, and we can get this expression for heat flux. So, this expression we will solve for non gray surfaces, where we are trying to find heat flux at a given wavelength. We have eliminated the radiosity from this relation using the above two equations. Using these two equations, we eliminate the radiosity and we have calculated the heat flux, the spectral heat flux. Once we know the spectral heat flux, the total heat flux can be calculated by integrating the spectral heat flux over all the wavelengths. So, the total heat flux q I at a given surface I is simply equal to integration from 0 to infinity, that is all the wavelengths, and the integrand is the spectral heat flux. Similarly, the total black body emissive power at a surface EBI is integration over all the wavelengths of the spectral emissive power. So, spectral emissive power is basically nothing but the Planck function. Now, these type of problems, if you try to solve this for each wavelength, so we have to solve for q lambda for all wavelengths. So, wavelengths may vary from 0 to infinity. We have to take some finite number of wavelengths. Each wavelength may be, the interval from 0 to infinity may be divided into lambda 1, lambda 2 and so on, okay, times lambda m. There may be 1000 wavelengths that you want to evaluate this integration through numerical scheme, or there may be millions of points. So, this method where we have to find spectral heat flux at large number of wavelengths, it is called line by line method. Where we have to find out the heat flux at each wavelength, and then we find the total heat flux by integrating over the spectral heat flux. So, there are two ways of simplifying this problem. We know that in this case the emittance is not continuously varying over wavelength, rather it is having a constant value in one spectral range and another constant value in another spectral range. So, the first approximate method to deal with this type of problem is called semi-gray approximation. For example, we have, let us say, a surface maintained at some temperature of, let us say, 300 Kelvin and irradiated by solar radiation. So, we know that the solar radiation contains most of its energy in the wavelength region from 0 to, let us say, 4 micron. Okay. So, most of the solar energy comes into this spectral range, while this plate which is maintained at 300 Kelvin will emit most of its radiation in the wavelength region greater than 4 micron. Okay. So, what we do is we split the problem into two parts. One part contains heat transfer, radiative heat transfer because of the solar energy which is in the 0 to 4 micron region, and the another part which is greater than 4 micron region does not contain solar energy, because we do not have solar energy in that spectral range. So, we have split the problem into two parts. We apply the energy balance equation for heat flux on the two parts of the spectrum. So, this is the first part for lambda, let us say 4 micron, and this equation is for lambda greater than 4 micron. Once we have solved these two equations for the heat flux, Now please note there is no wavelength here because the emittance is assumed to be constant. So, we have a value of emittance epsilon 1 and here we have the value epsilon 2 and which is constant over the wavelength region less than 4 micron or greater than 4 micron. So, the lambda does not appear here because we have assumed that the spectrum can be divided into two regions, each region considered to be gray. Once we have calculated the heat flux, the total heat flux Q I is simply the heat flux Q 1 I plus Q 2 I, that is the radiative heat flux from the two semi gray approximated fluxes. Okay. So, the two regions lambda less than 4 micron gives you heat flux Q 1 I and the other region lambda greater than 4 micron gives you flux Q 2 I, and we add the two components and we get the total radiative heat flux. So, this method is called semi gray approximation. We will solve one problem to demonstrate how a non gray surface basically can perform or increase the efficiency of a collector. Now, this problem of solar collector we have been doing, we have solved it for a number of cases. We have seen this solar collector problem on without reflector. So, this problem we have seen that without reflector it performs poorly, very poorly. Without reflector the efficiency is very poor. We have also solved this problem with a gray and diffuse reflector. So, we have done that gray diffuse reflector, and we have seen that in previous lectures that once we put a gray diffuse reflector, some part of the energy is actually reflected towards the plate while some part of the energy is reflected back into the atmosphere. So, this plate, gray diffuse plate, significantly improves the efficiency of the collector plate, but the efficiency can further be improved by putting a mirror. So, the advantage of putting a mirror is that it reflects only in a certain direction, that means it reflects most of its energy towards the collector plate and not towards the atmosphere. So, that is the advantage of mirror, which is basically a specular reflector. Now, the fourth type of modification to this problem that we are going to solve today includes non gray reflector. So, non gray reflector, it is diffuse, we will assume diffuse, but it is non gray. So, that means some part of the energy will indeed be reflected back to the atmosphere. So, first of all let me give you the governing equations we just learned. So, the governing equation for this problem is Q 1 or basically Q I 1 upon epsilon 1 1 minus 1 by epsilon 2 1 F 1 2 Q 2 1 is equal to minus H naught 1 1 plus E B 1 minus F 1 2 E B 2. This is the first equation, and for surface 2 Q 2 1 F 2 1 Q 1 1 is equal to minus H naught 2 1 plus E B 2 minus F 2 1 E B 1. So, these two equations have been written for the two surfaces for the spectral range lambda less than 4 micron, and we know that within that spectral range both the surfaces will not emit any radiation. The emission from both the surfaces will be in wavelength range greater than 4 micron. So, these quantities can be neglected, and H naught 1 is simply equal to q sun cos theta, and H naught 2 1 is equal to q sun sin theta. So, our equations now simplifies to q11 epsilon 11 minus epsilon 21 minus 1 f12 q21 is equal to minus q sun, or let us just write q or q sun cos theta, let us call this equation 1, and q21 by epsilon 21 minus 1 by epsilon 11 minus 1 f21 q11 is equal to minus q sun sin theta. This is equation 2, and these equations are for lambda less than 4 micron spectral range. Now, similar equations similarly for lambda greater than 4 micron we can write as q12. So, remember the superscript here represents the spectral range minus 1 f12, the view factor does not change, is equal to EB1 minus f12 EB2. So, here EB1 and EB2 are non-zero because two surfaces will emit and absorb within this spectral range, while the solar radiation coming from outside is taken 0 because very less contribution will be there in this spectral range. And similarly for surface 2, f21 q12 is equal to EB2 minus f21 EB1. Let us call this equation 3 and this equation 4. So, we have 4 equations and we have unknowns here, 4 unknowns q11, q12, q21, q22, and there is another unknown here EB2. Okay. So, we need one more equation. Okay. So, let us see how we will solve this. So, to solve this we will take a special case where epsilon 1 1 is equal to 1.0, and let me just and epsilon 2 1 is equal to 0 for lambda less than 4 micron, and epsilon 1 2 is equal to 0 and epsilon 2 2 is equal to 1 for lambda greater than 4 micron. That means the surface act as a perfect black body, perfect absorber, or they act as a perfect reflector. Surface 1 act as perfect absorber for lambda less than 4 micron, and it act as perfect reflector for lambda greater than 4 micron. So, we will put these values in the governing equation. So, let us add equation 1 plus f12 times equation 2, and we get, when we do that, q11 minus 1 f12 q21 plus f12 q21 upon epsilon 21 minus 1 by epsilon 11 minus 1 f12 f21 q11 is equal to minus f12 q sin theta minus q cos theta, where q is basically q sun, and on simplification this gives you Q11 upon epsilon 11 plus F12 Q21 minus epsilon 11 minus 1 F12 F21 Q11 is equal to minus Q F12 sin theta plus cos theta. Okay. So, this is what we have got, and we can put now epsilon 11 as equal to 1. So, we get Q11 plus F12 Q21, and then the second quantity becomes 0 is equal to minus Q F12 sin theta plus cos theta. So, let us call this equation as equation number 5. Now, similarly, we will write equation 3 times F21 plus equation 4. Adding these two equations, we get Q22 plus F21 Q12 is equal to 1 minus F12 F21 EB2. So, let us call this equation as equation number 6. Okay. So, now you should note that for lambda less than 4 micron, the reflector plate epsilon 2 1 is equal to 0. That means it is a pure reflector. Whatever solar energy falls on this reflector plate, all of this energy is reflected back. So, for this case Q21 will be equal to 0. Okay. So, all the energy basically is reflected back, and we get Q21 is equal to 0. So, in this expression Q21 will be equal to 0, and we get Q11 is equal to minus Q F12 sin theta plus cos theta, and this value given Q is equal to 1000 minus 1000, F12 is 1 by 4 sin 30 plus cos 30, and this value comes out to be minus 991 watt per meter square. Okay. So, in the range lambda less than 4 micron, the energy absorbed or energy flux on the collector plate is minus 991 watt per meter square. And how about Q12? Now, Q12 is basically the energy exchange with the collector plate in the spectral range lambda greater than 4 micron. In the 4 micron region, there is no solar radiation coming, and that is why Q12 will be simply equal to 0. Q12 will be simply equal to 0, and that is why we get Q1 is equal to Q11 plus Q12 is equal to minus 991 watt per meter square. So, this is very high collector efficiency for the semi gray approximation. If the plates are not semi gray, if the plates are gray, that means they absorb and they emit radiation or all over the spectral range, then what we will get is Q1 is equal to EB1. Now, the energy will be emitted by the plate minus Q cos theta. So, outgoing minus incoming, and this will be equal to 5.67 into 10 to the power minus 8 Stephen Boltzmann constant, and the temperature of the surface is 350. So, 350 power 4 minus 1000 cos 30, and this value comes out to be minus 15 watt per meter square, which is negligible. So, just by making the plates semi gray, we have increased the collector efficiency significantly. On the other hand, if we take gray plate, gray collector plate without reflector, then our flux will be Q1 is equal to simply minus Q cos theta, and that will be equal to minus 866 watt per meter square. Okay. So, this is non-gray collector plate without reflector, and this is plates are gray with no reflector. Okay. So, both the cases, if we do not assume reflector, does not create the much difference. The biggest difference in the collector efficiency is coming by making the collector plate as non-gray. Just by making the plate non-gray, we have increased the efficiency from minus 15 watt per meter square to minus 866 watt meter square without reflector, and minus 991 watt per meter square with the reflector. So, this was an example on semi gray approximation method for non gray plates. There is another approximate method, and the method is called band approximation. So, here what we do is now in the previous example we have a typical case where emittance was constant over only two spectral ranges. So, we have what we called 0 to lambda critical, or let us say lambda c, and then lambda c to infinity. Okay. We have only two ranges. So, we could apply the semi gray approximation. Now, it may happen many times that the wavelength region may not be so benign, our emittance value may actually vary like this or approximated like this. So, let us call this 0 to lambda 1, lambda 2, lambda 3 and so on. So, what we have in this case is basically what we call band approximation. So, in different bands. So, lambda 1 to lambda 2 is basically a band, okay, spectral band. So, in different bands we have a gray value or a constant value of emittance, okay, but there may be more than one or two such bands, okay. So, there may be multiple spectral bands. So, let us say we have m number of such spectral bands, spectral intervals. So, what we do is we take the equation of radiative heat transfer for non-gray plates, that is the spectral heat flux, for the equation of spectral heat flux, and what we do is we integrate this equation over wavelength region 0 to infinity. Now, what we do is basically we have to find out the total heat flux, which is basically equal to the spectral heat flux integrated over all the wavelength region. Now, what we have done is we have divided this integral into number of integrations 0 to let us say lambda 1 q lambda I d lambda plus lambda 1 to lambda 2 q lambda I d lambda plus lambda 2 to lambda 3 q lambda I d lambda and so on. Okay. There may be m such bands. Okay. So, what we have done is we have split the interval or in the integration the spectral integration into number of small intervals. Okay. Now, each of these intervals do not overlap, that is the prime conditions. So, 0 to lambda 1 and lambda 1 to lambda 2, these spectral intervals do not have any overlap. So, once we do that, we can assume that the q lambda is independent of lambda for each spectral interval. That means, within each spectral interval the flux q does not depend on wavelength. So, this can be just taken out of the integral and we can write down this as q 1 I, or let us say use a superscript here q 1 I plus q 2 I and so on up to m bands q m I. Okay. So, our heat flux is basically summed over all the spectral intervals. So, q I total heat flux is basically sum m is equal to 1 to capital M spectral intervals or bands and heat flux, the average heat flux over each band. Okay. So, that is what we have basically done. So, the heat flux q lambda I can be written as q I m over epsilon I m, where now the emittance also is constant over the each spectral interval. So, it can be taken out of the integral, and we have on the right hand side E b lambda I. Now, once we have to calculate this E lambda I over a spectral interval or band from lambda 1 to lambda 2, this non dimensional or parameterized black body function appears. So, E b lambda I integrated from lambda 1 to lambda 2 can be written in terms of difference between the parameterized black body emissive power. So, this lambda 1 to lambda 2 E b lambda I is simply equal to f function at lambda T I minus f function lambda 1 T I. Okay, so, that is the thing we have incorporated in this equation. So, our final equation for this band approximation becomes f lambda m T I minus f lambda m minus 1 T I minus j is equal to 1 to n. Similar thing for all the emitting surfaces, f lambda m T j, where T j is now the temperature of the surface j, minus f lambda m minus 1 T j. So, this represents the emissive power within that spectral interval. Okay. So, this is how we can apply the band approximation method to solve non-Gray problems. Semi-Gray method was relatively easy. Band approximation method, because of a large number of bands, may become little more complicated than the semi-Gray approximation. So, thank you for your patience. In the next lecture, we will discuss about combined mode heat transfer, where conduction and convection is combined with radiation, and we will see how in different applications this combined mode heat transfer may be useful, and how to evaluate the governing equations for these type of problems. Thank you.